Welcome back. In this video, I'll talk through example 1.20 from the section 1.2 of our text, negation, conjunction, and disjunction. So in this section, we learn about four different types of ways to combine statements and open sentences together. And if you haven't yet, be sure to read through the first part of the section where we define all of these operations on statements and open sentences so that you know what we're talking about in this video. In this example, we're given these two open sentences, P of n and Q of n. In part A, we're asked when P of n is true, for what values of n is P of n true. And here our domain, we should specify our domain. Again, you might have to read carefully, make sure to pay attention to what the domain is for any open sentence. Here we're dealing with not positive integers like the last example, but rather just integers. So for each of these, n is an integer. So this one we want to know, when is P of n true? For what values of n is P of n true? What values make P of n true? So we need n cubed minus n to equal 0. Well, I can play around with that, n cubed minus n. You might think, you might see some immediately, like 1 would work. That certainly works, but there are some other ones that work. One way we can see all of these that work, again, is to think of this like a polynomial that I'm finding the roots of. And so rather than just kind of guess and check, we could factor this. So I can factor an n out. We get n times n squared minus 1. And then n squared minus 1, this is a difference of two squares. So if you're taking calculus or have taken calculus, hopefully you've seen this enough times to know how to factor a difference of two squares. But it's not too hard. I'll show you how to do this. N minus 1, n plus 1. And you can see if you FOIL that out, you'll get n squared minus 1. In general, it's the square root of this term minus the square root of this term times square root of this term plus the square root of this term. So we have this completely factored, and we want that when this is equal to 0, so that gives us three solutions, right? We have a cubic polynomial. So this tells us n equals 0, or n equal 1, or n equals negative 1. Make this statement true. Make P of n true. And false otherwise. False for all other integers. So we have that one solved. P of 0 is true, P of 1 is true, P of negative 1 is true, P of any other integer is false. So moving on, we want to know when is Q of n true. Again, for which integers n is Q of n true. Q of n is 3n minus 2 squared greater than or equal to 20. Now, what we could do here, we could proceed like this, only I would need to first bring this 20 over. We'd find roots, and this would be similar to example 1.9, where we could graph the function, say, and find when it's greater than or equal to 0 once I move this negative 20 over. But we could also just think about this a little bit. So I could try this for a few values of n. So what about like Q of 0? Let's start with 0. Q of 0 would be 0 minus 2 squared. That would be 4 greater than or equal to 20. That's false. Q of 1 would be the statement. So I'd have 3 minus 2 in here. That's 1. Squared is 1. I'd have 1 greater than or equal to 20. That's false. I can do sort of just a quick check, right? Just keep checking these. Q of 2, I'd have 6 minus 2, that's 4, that's 16, greater than or equal to 20. That's a false statement. And maybe you can guess now, when I get to 3, Q of 3, I'd have 9 minus 2, that's 7 squared, 49, greater than or equal to 20 would be Q of 3, and that is true. And it's not too hard to see now, this is clearly increasing 3n minus 2 squared, that's an increasing function. for positive integers. And so once I get past, so anything 3 and above will be true. So I can say Q of n true for n greater than or equal to 3. Is that all of them? Well, no, maybe you noticed this deal going on here where I plugged in 0, I got 4, and then it went down to 1, and then it started increasing. And you should recognize this as a quadratic function, and so it should be we should be able to keep getting smaller or get into the negatives and get this to be greater than or equal to 20 as well. So I could try, say, -1. Let's try out Q of -1. So there's one conclusion. Q of -1 would be what? -5 might, wait, no, let's check that. -3 minus 2, yeah, that's -5 squared. That's 25. So we'd have 25 greater than or equal to 20. That's true. And just think about if I plugged in negative numbers less than or equal to -1, like -2, I'd get something even bigger, or I guess less than -5 here. When I square that, that'll be bigger than 20. And so Q of n true for n less than or equal to -1. So in summary here, Q of n is true when n is greater than or equal to 3, or n is less than or equal to -1, and false otherwise. Cool, so that's part B done. Now we get to really the subject of this section, which is what happens when we combine statements and open sentences together. So what we're asked to do now is find when P of n or Q of n is true. Also, and the conjunction operator, and also, what else did we want to do? XOR, the exclusive OR operation between these two. But we'll just take these in turn. So P of n or Q of n. So remember, when I combine two statements with an OR operator, this statement, this new statement I get out, P of n or Q of n, is true when one of the two are true or both of them are true. So now going to our data here that we have about P of n and Q of n, and when they're true, I just need either P of n to be true or Q of n to be true in order to make this statement true. So let's see, P of n was true for 0, 1, -1. So that'll make this statement true, 0, 1, and -1. And then Q of n was true for n greater than or equal to 3 and n greater than or equal to -1. So that's going to cover a lot of possibilities. The only things where Q of n is false, right, would be 0, 1, and 2. So Q of n is false when n is 0, 1, or 2. Notice P of n is true, though, when n is 0 or 1. So it seems like the only thing that would make this false is if n is equal to 2. Notice Q of 2 was false, and P of 2 was false. So P of 2 or Q of 2 is false, since both of them are false here, and true otherwise. So for all other n, P of n or Q of n would be true. So that's kind of cool. We're able to figure that one out. P of n and Q of n. So the conjunction operator. Remember, for the conjunction operator, I need both P of n and Q of n to be true for the same value of n in order to make this, the statement I get out, true. So I'm going to look over to my data again and find out what makes both of these true simultaneously. So again, P of n true, 0, 1, and -1. So -1 does make Q of n true, so it seems like P of -1 and q of negative 1 is true. Is there anything else that would make this true? Well, n equals 0, n equals 1, that would be the only other things that I would have to check because I need p of n to be true. But 0 and 1 do not make q true. So p of n and q of n is false for all other integers. So lastly is the exclusive OR operation. So I'll write this over by the OR operation. So exclusive OR, in this class we write with the O plus symbol. In logic, or in some other areas, you might see this written XOR, and I'll sometimes refer to it like this, XOR. In fact, if you're programming, that's what I've seen used for this operation. So P of n XOR Q of n. So remember, this is true when one of the two is true, but not both. So I can't have both being true. That would lead to this statement being false. So let's see. P of n or Q of n was true for everything except for 2. So that's sort of where I start with, is everything except for 2 I need to think about. But then I don't want both of them to be true. So that is, I need P of n and Q of n to be false. So that's another way to think of this exclusive OR operator. It's asking when the OR operation is true and the AND operation is false. I need both of those things to be true in order for the XOR to be true. So like this is true for everything except for 2, but P of n and Q of n, that's true just for -1. So for instance, P of -1 XOR Q of -1. Here, P of -1 or Q of -1, or maybe I'll say it like this, P of -1. P of -1, let's go back. P of -1 is true. Q of -1, when was Q true? Q of -1 was also true. Right, so both of them are true here. That's why the conjunction was true. And so this is false. So we gotta, right, this isn't a super easy problem to figure out when this XOR statement is going to be true. So let's see. Again, I need this to be true, which happens everywhere except for 2. And I need this to be false, which happens everywhere except for -1. So it looks like P of n XOR Q of n is true when n is not equal to 2, because then the OR operation would be false. And n is not equal to -1, because that makes the AND operation true. And in that case, right, as we saw, we'd get a false. So it looks like this is the only two that don't work. We can do a quick check. Maybe let's try 0. It doesn't hurt to go through some of these in detail. Q of 0. So in this case, we can check P of 0. P of 0 is true. And Q of 0 is false. And so this would make this true. And so, yeah, we just checked one of these, but by the logic we went through there, this would be our answer. So long as n is not 2 and not -1, then P of n XOR Q of n would be true. Okay, that's it for this video. Next time.